Hello and welcome everyone to first section in chapter 2, and that are direction fields. And so you're going to see that this first part isn't going to be anything that's going to be brand new. We're going to talk about our direction fields. And so a derivative of dy over dx of a direction function, differential function y is equal to y of x gives slopes of tangent lines at points on its graph, given dy over dx equals x of xy. The function f is called the slope function or rate function. If we systematically evaluate f over a rectangular grid of points in the xy plane and draw linear element short line segments at each point xy of the grid with slope f of xy, then we will get a direction field of the differential equation. Direction field suggests the shape of a family of solutions of the curve of the differential equations. So here we have example 1. Sketch a direction field for the given differential equation. And here are the differential equation is y prime equals y minus x. Now, I did not want to have to do this in front of you because it's going to take a long time to do all these. But what I did was I made this little plot on the left, and these values over here, these are my x values, these are my y values. And what I did is I made a chart because I knew that y prime equals y minus x is going to hold to a certain pattern. And it's made this easy. When I did -3 minus -3, for the first one, I get 0. And as we go along that diagonal, we're going to get 0. And the same thing happens with every single combination that's a difference of 2 or difference of 1, and so on and so forth. And so I went ahead and did my, instead of having to do f of -3, -3, and get 0, all I did was made a chart. And so you're going to find that making a chart like that can make your work a lot easier. Now, over here, I just went ahead and sketched the slope field over here. And you notice that, I'm not going to be too harsh when I'm grading this. When I grade your slope fields, just make sure that you try to denote how much, one's steeper than the other. But like right here, this was -6. Oops. This is -6. That's -5. I try to denote just, a little bit of difference right there. Again, it's not going to be perfect just as long as some type of shape. You've done direction fields, slope fields before, so this section, this part of the section is not going to be too difficult. Now, something that's going to be new for you are autonomous first order differential equations. So what an autonomous first order differential equation is an ordinary differential equation in which the independent variable does not appear explicitly is said to be autonomous. So when we have a differential equation, dy over dx, the function on the right hand side is going to be in terms of the independent variable. I'm sorry, not the independent, but the dependent variable. So all of these are in terms of y. And so you notice that the independent variable isn't going to appear on the right-hand side of our differential equation. So here we have dy over dx, independent variable is x, and so our, what it's equal to is going to be y cubed plus 10. Again, you don't see the x there. dp over dt, t is going to be the independent variable. Notice, it doesn't here on the right-hand side, and then over here on the right, same thing. Our lowercase t does not appear for what our differential equation equals. So that's what is an autonomous first order differential equation. It's going to be, or a differential equation is going to be pretty much, what's the word I'm looking for? It's going to be defined pretty much by, all of its dependent variables. So, for definition, a real number c is a critical point of the autonomous differential equation if f of c is equal to 0. A critical point is also called an equilibrium point or stationary point if c is a critical point, then y of x equals c is a constant solution to the differential equation. Now, why is that? Well, if we substitute in C into our differential equation and get 0, it's a critical point. So my differential equation at that point, so we could say, since this is going to be y of x, we'll say dy over dx. So dy over dx at that value is equal to 0. Right, that's what our differential equation is. Then you can take this from separable equations, which we're going to talk about in the next section, so tomorrow. When we try to find a solution to this, we're going to get y is equal to just some constant. And so what's happening at that point is that when our differential equation is going to be tending towards one of those critical points, and so that's why it's called an equilibrium point, because as we're going along the differential, or our slope field, which is just a bunch of slopes based off of the differential equation, they're going to tend to some number. And so that's why if C is a critical point of our differential equations, then the solution is just going to be y of x is equal to C. It's just going to be that value of C, which gave us our differential equation equal to 0. So example 2, consider the should I go ahead? We'll stop here and then we'll go on to the next one.